Hey, 17B students, welcome once again to my guest room. You can see there's some pillows and hats on it. My wife has some big hats. Chill. Kind of great. Great for the beach. Like that. Anyways, we're not here to play around. We're here to do some math. So let's get started. So this is to take the place of class on Friday, October 20th. I should switch on the seat here. Okay, here we go. And so we're going to talk about mostly his methods of integration and when to apply them. And I have this handout that I'm going to post on Canvas as well. I'll kind of show it to you right now. It looks like this. It's a 21B handout, but it's been modified for 17B. So basically the idea is to figure out what way we want to integrate something, we're going to look at what kind of integral we have. And the categories are very broad here. So I'm fixing this a little bit. The categories, I would say, start off with algebra. So meaning, does the integral look like it's just x to powers? No exponentials, no trig, no logarithms, just x squared, square root of x, all sorts of things like that. Rational functions, but nothing that has any other kind of function. And there's a lot of stuff, in that category, which we'll talk about. And after that, we'll talk about having just trig. And then after that, we'll talk about mixtures where a lot of your U sub comes in. So we'll start with the basics and hopefully I'll cover most things in not too much time here. So first off, we got algebra. Let's give this a big I for like the first section here. So algebraic integrals, meaning no trig, no logarithms, no e to the x's. Just x to a power, and the power can be anything. So the first thing we ask really is just, can we make the integral an exponent problem? Now, I know when I say exponential, I usually mean e to the x, but when I say exponent, I mean x to a power. In other words, can we simplify our integral? Let's look at some examples. For example, the integral of 2x plus, I'm going to change it a little bit, 2x plus 5 squared. Yeah, we could do a u sub here, but this one's so kind of small in that we can multiply that pretty easily that we should just write it as the integral of 2x plus 5 times 2x plus 5. And 2x plus 5 times 2x plus 5 is 4x squared plus 10x plus 10x is plus 20x plus 5 times 5 is 25. We can anti-differentiate that. We're going to get 4x to the third over 3 plus 20x squared over 2 plus 25x plus a constant since it's indefinite. And then you could simplify that. I don't think that's really important, but we get 4x cubed over 3 plus 10x squared plus 25x plus c. Or maybe, pardon me, maybe your integral looks like some sort of, let me try and keep my papers. Let me keep things in order here because I will scan these in a second here, in more than a second. The other question, or maybe we have something that looks like the integral of, what do we got here? Sure, 4x cubed plus 7x plus 9, all divided by x squared. In the same sort of way, we can make this an exponent problem, meaning x to a power, I should say a power problem, a power of x problem, by dividing each term by the denominator. And let's make this a definite integral just to kind of make it a little bit different. Let's say this is the integral from 1 to 3. So I can simplify this by writing it as the integral from 1 to 3 of 4x cubed over x squared plus 7x over x squared plus 9 over x squared, which I should then simplify as the integral from 1 to 3 of 4x plus 7 over x, or if you prefer 7 times 1 over x. I'm going to try and be more on camera here. And then plus 9 times x to the negative 2. I prefer not to write 1 over x as x to the negative 1 because it's easier for me to remember that the antiderivative of 1 over x is the natural log of the absolute value of x, whereas the antiderivative of x to the negative 1 just doesn't seem as obvious to me that it's the natural log of the absolute value of x. So here, anti-differentiating, we're going to get 4x squared over 2 plus 7 times the natural log of the absolute value of x plus 9x to the negative first divided by negative 1. I don't need a plus c because it's definite. I'm going to evaluate from 1 to 3. I would make my life a little bit simpler here. 4 divided by 2 is 2x squared. I can drop the absolute value here because both the numbers I'm going to plug in are going to be positive, so I don't really need that anymore, although it's totally fine to still write it. And then finally, 9 divided by negative 1 is negative 9, and x to the negative first is the same as dividing by x to the first. So I write this as negative 9 over x. Plugging in, I'm going to get 2 times 3 squared plus 7 times the natural log of 3 minus 9 divided by 3 minus 2 times 1 squared plus 7 times the natural log of 1 minus 9 divided by 1. Natural log of 1 is equal to 0. So we're left with 2 times 9 plus 7 times natural log of 3 minus 3 minus, let's see, that's 2 minus 9. So 2 minus 9 is negative 7. Again, the simplification is not really what's important here, but since we're doing the problem, I might as well do it right. We've got 18 minus 3 plus 7 plus 7 natural log of 3. That's 15 plus 7, that's 22 plus 7 natural log of 3. Cool. So if you have just x to a power or powers of x, and you can write it as, you know, a bunch of stuff added or subtracted together, where it's x to a power, we can just anti-differentiate it straightforward. But usually it's going to be more complicated than that. So let's look at some other examples. So the next thing I usually look for, if I have really any integral, is can I see that the derivative of one part is equal to another part? For example, if I had the integral of, sure, let's say 8x plus 2 times 4x squared plus 2x plus 13 to the, that's a 13, believe it or not, to the negative 7th power dx. I suppose I could have also actually written this, I might have written this first as the integral of 8x plus 2 divided by 4x squared plus 2x plus 13 to the positive 7th power. That's probably how the integral would actually originally be expressed. And if I see that the derivative of one of these pieces, in this case, 4x squared plus 2x plus 13. Sorry, my 13s often look like b's because I write them so sloppily. The derivative of that is 8x plus 2. Or in other words, the derivative of one piece is equal to another part. If that's the case, that's a really good time to use U substitution. So our choice for U would be this thing right here. So we have that U is equal to 4x squared plus 2x plus 13, and our du dx is equal to 8x plus 2. So that du is equal to 8x plus 2 times dx. And then we rewrite the integral. So that's our u, that's our du. So we can rewrite this as, in fact, I like to do this, I like to circle that and be like, oh, that is equal to du. Get the integral of du over, that's u right there, u to the 7th. And then we see that it's another kind of power problem, like a variable to a power, just like the previous stuff. So this would be equal to the integral of u to the -7 times du, which is then u to the -6 divided by -6 plus c, which I would first rewrite as, let's write it over here, -1/6 times u to the +6. And people tend to prefer positive powers and putting the negatives out in front. And then finally, replacing u with what it's equal to, u is equal to 4x squared plus 2x plus 13. So this is going to equal -1/6 times 4x squared plus 2x plus 13 to the 6th power plus c. It would also be totally fine to write this as 4x squared plus 2x plus 13 to the -6th power divided by -6 plus c. It just looks a little less nice. It doesn't have to look perfect. All right, should we do one more u substitution problem? Probably, yeah. Let's look at one more. Because sometimes the choice for u is not going to be perfect, right? Sometimes you're going to pick u and the derivative is not exactly going to show. I mean, you're going to be off by like a constant multiple. So let's look at something like, for example, we'll make this one a definite integral just so it's a little more interesting. Let me come up with something here. Let's say we have the integral of, sure, the cube root of, I've made my life challenging by picking a cube root here. Let's say the cube root of x to the 4th plus 1 dx, and we have an x cubed out in front, and x is going from, sure, 0 to, sorry, I've chosen poorly here. I want this to be a nice cube number. Sorry, I was trying to think of something nice and now it's going to be terrible. That's fine. Let's make it, we'll just live with it being a terrible number. Let's say it's the integral from 0 to 1. Yeah, 1, sure, why not? 1. Sometimes you have terrible integration and that's just how life goes. So, step 1, I see that picking u equal to x to the 4th plus 1, which is a good choice because not only is its derivative essentially in the integral, off by a constant, it's also stuck inside this cube root. That's making it an excellent choice. So I'm going to say that du dx, the derivative, is equal to 4x cubed. And then I personally would say multiply both sides by 1/4 and also both sides by dx. So that 1/4 du is equal to x cubed times dx. I might rewrite this just slightly so I can have the things next to each other that I like. It makes it easier for me to see it, but you don't need to do this. But you can rewrite this as the integral from 0 to 1 of the cube root, or if you prefer, x to the 4th plus 1 to the 1/3 times still x cubed times dx. Just so that then you can say, oh, look, my x cubed times dx, that's equal to 1/4 times du. And my x to the 4th plus 1, that is equal to u. So now I can rewrite my integral. Ooh, we should also change the limits of integration. If x equals 0, u is equal to x to the 4th plus 1. So u is going to be 0 to the 4th plus 1, which is 1. And if x equals 1, u is equal to 1 to the 4th plus 1. 1 to the 4th is 1, plus another 1 is 2. So our new limits of integration are going to be from 1 to 2 of u to the 1/3 power times 1/4 du. I bring that 1/4 out in front. And then we can use the antiderivative of u to a power. We're just gonna, just like all the other times so far, we're gonna add 1 to the power and divide by the new power. So you're gonna get u to the 4/3, and instead of dividing by 4/3, we're gonna multiply by 3/4. Evaluated from 1 to 2. So then we're gonna get 3 times 1 times 3 is 3, 4 times 4 is 16, so 3/16. You can actually hold this constant out in front, so you can say it's like 1/4 times 3/4 times just u to the 4/3 evaluated from 1 to 2. That's totally fine. Doing that, we're going to get 2 to the 4/3 minus 1 to the 4/3, which is just 1 to any power is 1. So if I was finishing this problem, I'd probably leave it as 3/16 times 2 to the 4/3 minus 1. And that's about as good as it gets. So if you happen to have just, again, right, what we call an algebraic type of integral where you have roots or powers of x, or no cosine sign, no exponentials, no logs. If you see something that can be the derivative of something else, that's usually a good indication that a u substitution is the right way to go. However, it's not always going to be the case. So there's a couple other things that come up. One other thing that comes up when it comes to algebra, let me make sure I've got all my stuff going on here. Yeah, cool. Is you might have to do some long division. Specifically, if you have a rational function. So this is only for rational functions. Oh, sorry, I should point out I've entered part C of this handout, which is tricks. Tricks is maybe not the right word, but techniques that feel kind of tricky sometimes. So we've got first long division. So for example, if you have something like the integral of, I don't know, x cubed plus 2 over x minus 1. And of course, I didn't plan very well ahead here. This is probably not going to turn out well. Such is life. Sometimes you make mistakes. But let's see what happens. So I'm going to do the long division. X cubed plus 0x squared plus 0x minus 1, right? That's, plus 2. Apologies. It's just edit it out. Not really. I'm not good at editing. So there's my thing. That's my dividend, the thing that's being divided into. And then x minus 1 is my divisor. X times, let's use a different color up here. X times x squared is going to give me x cubed. And the x squared times -1 is minus x squared. If we subtract, 0x squared minus x squared is 0x squared plus x squared, which is x squared. Bring down the next term. Repeat the process. X times x will give me x squared. So x squared, x times x is x squared. X times -1 is minus x. Subtract. X squared minus x squared is 0. 0x minus x is positive x. Bring down the 2. X minus 1 times 1 will give me x plus 2. Oops, I want to do this in red. Sorry. Doesn't really matter, but kind of consistent. 1 times x minus 1 is x minus 1. Subtract. X minus x is 0. 2 minus 1 is 3. So what we can say here is that our fraction x cubed plus 2 over x minus 1 is equal to this quotient x squared plus x plus 1 plus the remainder divided by the divisor. And then we can say that the integral of this is equal to the integral of that. So this integral is going to be equal to the integral of x squared plus x plus 1 plus 3 divided by x minus 1, which is going to end up equaling x cubed over 3 plus x squared over 2 plus x plus, technically this 3 over x minus 1 needs a u substitution if you want to do it that way. I don't think you need to. We can think of this as 3 times the integral of 1 over x minus 1. And the integral of 1 over x minus 1 or 1 over x plus anything is just the natural log of x plus or minus that. It has to be x to the first, though. That's going to be a 3 times the natural log of the absolute value of x minus 1. Let's see. Let me do something. I need to, getting like 1,000 text messages here. I would like to mute this conversation. One moment, please. I'm on a group text with my wife and our very good friend, and they're texting each other a lot. I'm like, I don't need to get all these notifications right now. So let's do one more long division one, because there's one other thing that happens a lot that's kind of annoying. And maybe a lot is a strong word, but happens occasionally. It's kind of annoying. So let's say we wanted to find the integral of, what have we got here? Sure, let's do that. Yeah. Sure, we can do this. Let's say we had 2x minus 3 over x plus 1. One way to do this is actually just to do a u substitution. It's not very fun, but it's fine. You can do a u sub letting u equal the denominator. If u equals x plus 1, the derivative of u with respect to x is just 1. So du is equal to 1 times dx. So certainly changing the dx to du is straightforward. Dx is just equal to du. X plus 1 is just equal to u, but the problem is there's leftover x's in my numerator. So what I have to do is then do what's called a back substitution. So I could do this and say, well, u minus 1 is equal to x, and then substitute that in for the x right there. So this integral is going to become the integral of 2 times u minus 1 minus 3 divided by u du. We simplify that. That's the integral of 2u. 2 times negative 1 is negative 2, minus 3 is negative 5 over u. If I divide each thing by u, 2u divided by u is 2, minus 5 over u is just 5 over u. We anti-differentiate, we get 2u minus 5 times the antiderivative of 1 over u is the natural log of the absolute value of u, plus c. Finally, substitute back in what u is equal to. You get 2 times x plus 1 minus 5 times the natural log of the absolute value of x plus 1, plus c. And that is a perfectly fine way of doing this problem. But I think it's easier to do this problem if you do polynomial division, because if the power on top is greater than, or I should say, not the power, the degree, right, the highest power. If the degree on top is greater than or equal to the degree on the bottom, then you can and probably should do polynomial long division. So if I do the division, 2x minus 3 divided by x minus 1, x times 2 is going to give me 2x, so 2 times x is 2x. 2 times negative 1 is minus 2. Subtract. 2x minus 2x is 0. Negative 3 minus 2 is, that seems like I might have made a mistake. Let me double check. Oh yeah, I should have been a plus 1 there. So how did I know I was making a mistake? Well, I was going to get negative 3 plus 1, which is negative 1, but I saw that I got a 5 over here, so I was a little bit, that doesn't seem right. And it wasn't right. That should have been a x plus 1, which means 2 times the 1 there is a positive 2. And then negative 3 minus 2 is negative 5. So we end up getting, if we rewrite our integral, the integral of 2x minus 3 over x plus 1 is equal to the integral of 2 minus 5 divided by x plus 1. And if we get to differentiate this, we end up getting 2x minus 5 times the natural log of the absolute value of x plus 1, plus c. And interestingly, these answers aren't exactly the same. If I actually multiply this out, I've got 2 times x and 2 times 1 is 2x plus 2 minus 5 natural log of x plus 1, plus c. These differ by 2, but really it's the fact that this constant and this constant actually differ by 2. So this constant here is c1, this constant here is c2, and this c1 plus that 2 is the same as that c2. So if you do an integral in a different way, like use a different method, and you end up getting a different answer, as long as that answer is only different by a constant, that is totally fine. It's a valid operation. So polynomial long division, as long as you have a rational function where the degree on top is greater than or equal to the degree on the bottom, then you probably should do polynomial long division before doing anything else. Then, sometimes when you do polynomial long division, you're still left with a rational function that is challenging to deal with. So typically, what happens sometimes with rational functions, and this is, let me relabel that. I'm at the lowercase I here now. Sometimes you have to use partial fractions. Again, this is all under the heading of just algebraic things, right? Powers of x, square roots, cubes, but nothing trigonometric, nothing exponential, nothing logarithmic. Certainly we've gotten answers that have been logarithmic. That's fine, but nothing that has had an integral with that kind of function inside of it. So I think this is the last thing in our list of, yeah. Oh, there's one other thing that's kind of annoying, but okay. This is almost the last thing in our list of methods that for algebraic intervals. So let's say we have something like the integral of, sure, 3x plus 1 over x squared plus 4x plus 3. Well, the degree on top is not larger than the degree on the bottom, so I don't get to do polynomial long division. And I can't do a nice u substitution here, right? If I let u equal x squared plus 4x plus 3, the derivative is not just a multiple of the top. The derivative is 2x plus 4, and that certainly is not just a multiple of 3x plus 1. So that's not going to fly. So then we have to look and see, well, does the denominator factor? And it does. We can rewrite 3x plus 1 over x squared plus 4x plus 3 as 3x plus 1 over x plus 1 times x plus 3. And then we're going to rewrite that as a over x plus 1. The notes are a over x plus 3. I guess I should be consistent with the notes just to be consistent. Plus b over x plus 1. And then we're going to multiply both sides by the common denominator. We're going to multiply the right-hand side by x plus 1 times x plus 3, and the left-hand side by x plus 1 times x plus 3. I guess I can do that. So on the left-hand side, that and that just cancel out. I'm left with the numerator 3x plus 1. On the right-hand side, we're going to get a times, well, if we distribute this here, the x plus 3's cancel, and we get a times x plus 1. We distribute here, we get b times x plus 3. And then I like to do what's called picking convenient values of x. So I can pick x equal to -1 because that's going to make this term go away. I get 3 times -1 plus 1 equal to a times 0 plus b times -1 plus 3. That's -3 plus 1, so -2 equal to -1 plus 3 is 2 times b. Dividing both sides by 2, I get b equal to -1. Similarly, I'm going to pick x equal to, you should think about it for a second and ask yourself, what am I going to pick for x next? Oh, it's going to be the thing that makes that part 0, so it's going to be x equal to -3. So over here, 3 times -3 plus 1 equals a times -3 plus 1 plus b times 0. You don't really need to write the b times 0 part, but it's good to observe at least. -9 plus 1 is -8. -3 plus 1 is -2, so we get a times -2. So a is equal to -8 divided by -2, which is +4. So then we can rewrite our integral, the integral of 3x plus 1 over x squared plus 4x plus 3 is equal to the integral of a over x plus 3 plus b, which was -1. You might write minus, but I already wrote a plus sign, so I'm just going to write plus -1 over x plus 1. The integral of 4 over x plus 3. If you really want, you can write this out to make it easier to see. I don't think you need to take this step, but you can write this as 4 times the integral of 1 over x plus 3 dx minus the integral of 1 over x plus 1 dx. If you really want to see the 1 over x plus something to get you the integral, which is the natural log of that denominator. So that's going to be 4 times the natural log of the absolute value of x plus 3 minus the natural log of the absolute value of x plus 1. Let's see. Okay. I would leave it like this. Some people prefer to compress this into one logarithm to bring this 4 up as a power and write this as the natural log of absolute value of x plus 3 to the 4th minus the natural log of the absolute value of x plus 1. And then combine those as the natural log of this divided by that. So write that as the natural log of the absolute value of x plus 3 to the 4th divided by x plus 1 plus c. I don't see any value in that personally, but you might see a textbook simplify something like that. So just be aware. Sometimes people do funky things with answers. Let's look at one other partial fractions example, because sometimes you have a repeated linear factor. You grab one of those. Oh, if I don't have an example, I'll just make one up. Totally cool. Yeah. So let's say we have something like, I don't want to make it too terrible, but let's say we have the integral of, I don't know. Let's say I'll make it a little terrible. Fine. Let's say we have the, yeah, I'm gonna make this one challenging more so we can see how the setup works, not so much how the solving works. But the solving is kind of a big piece too. So you might, if you decide this one gets too long, you might just want to skip it. So let's say we have the integral. Let's say our denominator is x cubed times x minus 1 squared. And then, so that's going to be a degree 5 in the denominator. And let's say the numerator, just for fun, is 2x squared plus x minus 3. I might regret this. We'll see. So clearly a U substitution is not going to work here. Although you should be on the lookout, right? Sometimes someone just as a quick aside here, someone's at one point could write an example like, I don't know, I'm going to give you the integral of, let me make something that's not too, yeah, let's say I had like x times x minus 1 squared on the bottom. Let me think about what that is for a second. Let me not write on the right one. Let's see. Sorry, brain. And I have let's say a 6x squared. Sorry, working on it. Minus 8x plus 2 on top. If you saw that, you might miss out on the fact that it's really a U sub. You might be like, oh yeah, look, the bottom's already factored. They're clearly indicating I should do a U sub, but they're lying to you. They're trying to trick you. So not that you like more, I would say normally if you see something factored on the bottom, that's generally a good indication that partial fractions is probably the way to go. But I'll point out that if you multiply at the bottom here, x minus 1 squared is x squared minus 2x plus x, sorry, plus 1, apologies. If you multiply that all by x, you get x cubed minus 2x squared plus x. And if you let that equal u, your du is going to be 3x squared minus 4x plus 1 dx. And if you multiply that all by 2, 2 times du is equal to 2 times all that, which is exactly 6x squared minus 8x plus 2. So this one, don't let yourself get fooled into accidentally doing a partial fractions process when it's easier to do a U substitution process. Again, it's not usually something that someone's trying to trick you with, but it could happen. So here we would end this problem by saying, well, this integral is going to equal the integral of, on top I have 2 du, on the bottom I just have u. That's going to be 2 natural log of the absolute value of u plus c, which ended up being 2. I should make some room here. So this integral is going to equal 2 times the natural log of the absolute value of u plus c. If you use partial fractions, you would still end up getting a very similar answer, although it would probably look more like if you factor this apart and broke it up into many logarithms. All right. Anyway, back to the problem we were actually doing. So this one's going to have a partial fraction decomposition with 5 pieces. We're going to write that 2x squared plus x minus 3 over x cubed times x minus 1 squared is equal to a over x cubed plus every lower power of x, so b over x squared, c over x down to the x to the first. We're also going to have a d over x minus 1 squared plus a e over x minus 1. Yes, this is terrible and probably not a reasonable question for you to be asked. Multiplying both sides by the common denominator, which is x cubed times x minus 1 squared. We know on the left-hand side, we're just going to end up with the numerator. So we're going to get 2x squared plus x minus 3. On the right-hand side, it's going to be a little bit gross. You're going to get a times x minus 1 squared plus b times x minus 1 squared, because when you multiply times that, the x cubed cancels. When you multiply by that, the x squared cancels, leaving an x and the x minus 1 squared. When you multiply here, just the x cancels, so you get c times x squared times x minus 1 squared. Multiplying here, the x minus 1 squared cancels, you get d times x cubed. And multiplying here, you get e times x cubed times x minus 1. All right, so let's go ahead and pick the two convenient values of x we have. We have x equal to 0, which is going to give us a -3 on the left, equal to an a times 0 minus 1 is -1 squared. That's a 0, that's a 0, that's a 0, that's a 0. So then we're getting -3 equal to a times 1, so -3 equals a. Great. Let's pick our other convenient value, which is x equal to 1. So plugging in 1 here, you get 2 plus 1 minus 3. I might get getting a 0 here. Equal to 0 plus 0 plus 0 plus d times 1 cubed. 1 cubed is 1 plus 0. So 2 plus 1 minus 3, that's a 0 equal to d. Sometimes that happens. Sometimes terms just don't end up being part of your integral. So we're not going to get this piece of our partial fraction decomposition is just going to be 0. Cool. Now we've reached the part of the game where we've run out of convenient values. And although you could start picking other values of x, it gets really messy, especially when there's still 3 more things to find. This is where I think we should do what's called equating coefficients. So if we were to multiply out in fact, let's just multiply it out, even though it's kind of gross, it's not that gross. So here's what we've got. On the left-hand side, 2x squared plus x minus 3. On the right-hand side, you've got a times x minus 1 squared is x squared minus 2x plus 1. Same thing there, but then you're going to multiply it by an x as well. So you're going to get b times x cubed minus 2x squared plus x. Same deal there, in fact. You're going to get I'm going to run out of room here, sorry. C times, instead of x squared minus 2x plus 1, you're going to multiply that by x to the squared as well. So you're going to get x to the 4th minus 2x cubed plus x squared. We already know d. Oh, you know what I should have done? I should have plugged in -3 for a. That would have been smart. Let's go ahead and do that. I know it's going to be kind of gross, but I can fix it there. That doesn't look too bad. And d is 0, so let's not even write that term. And then you're going to get e times x to the 4th minus x cubed. And now we're going to look at the coefficients of different powers of x, usually starting with the highest power of x. So the highest power I see is x to the 4th. So x to the 4th, well, I have 0x to the 4th on the left. And I have a c times x to the 4th plus an e times x to the 4th. So 0 equals c plus e. And I'm all out of x to the 4th. So I don't know what c or e is yet. So I'm going to move on to the next highest power, x to the 3rd. So on the left-hand side, still no x to the 3rd. On the right-hand side, I don't have an x to the 3rd here. I do have one there, though, so I get a b times x to the 3rd. I have one here. I'd have a c times -2 times x to the 3rd, so that's going to be a minus 2c. And I have an e times -1 times x to the 3rd, so I'm going to have a minus e. Okay. I could probably do something with those two, but I probably need one more equation. So let's get one more equation. So let's look at the next highest power, x squared. Look at x squared, that's where things are going to get messy because there's a lot. So on the left-hand side, the coefficient of x squared is 2. On the right-hand side, the coefficient of x squared is a -3 times x squared. A b times -2 times x squared, so a -2b. A c times 1x squared. And a no e. Great, I can definitely use these 3 equations and 3 unknowns to solve for everything here. So first, what I would observe here is, using this one, c is equal to -e. So I can plug that in for both of these equations here. Yeah, I guess, I mean, do I really want to do that? Yeah, I guess that works. It's kind of, sure, it's fine. Yeah, I guess or I could have said e is equal to -c, just so I had, these ones will have b and c. So let's do that instead. Let's say -c is equal to positive e. So plugging in a negative, I guess I didn't change it, fine. Plugging in a -c for e, I'm going to get 0 equal to b minus 2c minus negative c is plus c. So that's going to be 0 equals b minus c. So that means b is equal to c. And I can plug that in here and get, let's add 3 over here, 5 equal to, if I plug in c for b, negative 2c plus c. Negative 2c plus c is negative 1c. So 5 equals negative c. Negative 5 equals c. I know it's kind of a lot. It's kind of gross. You probably wouldn't have to do one like this. But if I do that c equals negative 5, c equals b, or b equals c, so b also equals negative 5. And then I know that e is equal to negative c, so e is equal to negative 5. Kind of terrible. But then we can totally rewrite our integral as the integral of negative 3 over x cubed plus b, which was negative 5 over x squared, plus c, which was negative 5, negative 5 0 over x, plus, and that just happened randomly, like I made this up on the fly, and then plus e over x minus 1. I don't want to rewrite this. I'm just going to point out that that's a negative 3 times x to the negative third, and that's a negative 5 times x to the negative 2. So when I integrate this, I end up getting negative 3x to the negative 3 plus 1 is negative 2 divided by negative 2, minus 5x to the negative 1 over negative 1, minus 5 natural log of the absolute value of x, plus 5 natural log of the absolute value of x minus 1, plus c. Yeah, you could simplify that, but come on, it's terrible. Let's be done with that. This video is getting kind of long. Maybe I should stop after the algebra and make a part 2. Not, I mean, like tonight, but like cut it up into bits here. So there's one more algebra thing that we should talk about, which I believe some of us have seen, which is the what's it called? Sorry, it's the algebraic substitution. Technically, some of you saw a trig substitution problem as well, where the teacher did that problem where they said like set x equal to tangent of t or whatever. We'll ignore that. The one thing you should know though, of course, is that the integral of 1 over 1 plus x squared is equal to the arc tangent of x. Let's see, or the inverse tangent if you like. Again, I'll point out it's still an algebraic integral, right? The integral is just powers of x and fractions. The answer is an inverse trig function. This can be more complicated, right? Oops, sorry, that's terrible. Let me see if I can refocus that. Okay, there we go. Cool. If instead you had the integral of like 1 over, say, 4 plus x squared, let's make it 9. I'm honestly terrible at doing this. I always kind of forget how you're supposed to do it. Yeah, here's what you're supposed to do. You're supposed to factor out a 9 from the bottom. There's other ways of doing this. This is the way I've seen to do it. So then the 1/9 comes out. You got the integral of 1 over 1 plus, instead of writing this as x squared over 9, we're going to write it as x over 3 squared. Okay, and then that's our choice for u. So we're going to do a u sub now. U gets to equal x over 3, or if you prefer 1/3 x, du is just 1/3 times dx. So 3 times du is equal to dx. Great, that's easy to replace. That's going to be 3 du. That's going to be u. So this ends up becoming the integral of, 1/9, the integral of 1 over 1 plus u squared times 3 du. Let's bring the 3 out in front. So we've really got 3/9 or 1/3 integral of 1 over 1 plus u squared. But we know that the integral of 1 over 1 plus x squared dx is arctangent of x. So the integral of 1 over 1 plus u squared du is the arctangent of u. So you end up getting 3/9, which is 1/3 arctangent of u. Let's see. which then plug back in what u is equal to, which was x over 3, and you get 1/3 arctangent of x over 3. Let's see. So that's how you deal with something like that. It's kind of a pain, but it is what it is. Finally, sorry, I know I got kind of off track here. That question often comes up. Well, and no, I'll just leave it at that. That was partial fractions. I guess this could be kind of a special thing on its own. It's like one of rho plus x squared is just kind of its own thing. And finally, the last thing in these algebraic intervals section is algebraic substitution. Or as some people tend to call it, power substitution. Well, you know, we left off with back substitution. So we'll talk about that too. So let's say we have this integral of x over the square root of, that's actually not what I meant to write. Fine, we'll look at this one anyway. So how many your brain gets started? Also, it's really hot. Let me turn on the air real quick here. I'm getting a little warm in this room here. You know, we're getting, oh, is it really? That can't be right. Feels warmer than that. All right, so I don't love the problem I've written, so I'm gonna change. Oh, I guess we can do that. Fine. Yeah, back substitution is not on this list here. I'm not surprising. Back substitution is certainly a thing. So let's do that first, and then we'll talk about the other thing. So what is it? 4. Let's say back substitution. I guess we already kind of talked about a back substitution problem when I was doing that problem that we could have done using either substitution. We use substitution and polynomial division because the powers are the same. That was an example when I did the substitution of a back substitution. Let's do one other one just so we can see it. So yeah, something like the integral of, sure, x cubed times x minus 1 to the 20th power. Here, I really want to let u equal x minus 1. I can make this more interesting, yeah, but we won't. So use x minus 1, du is equal to dx. So great, everything's taken care of. That's my u, it's my du. But my x cubed, I have a leftover x, or x to a power. So I solve for x here. I say u plus 1 equals x, and then I jam that in for x there. So that x is u plus 1. So x cubed is going to be u plus 1 cubed. So rewriting this integral, it's going to be the integral of u plus 1 cubed, which is maybe larger than I wanted to go, times u to the 20th times du. And then I have to multiply out u plus 1 cubed. Not my favorite. It's fine. It's going to be u cubed plus 3u squared plus 3u plus 1 times u to the 20th. And then we have to anti-differentiate each one of those and get u to the 20th. Sorry, we have to multiply that out before we anti-differentiate. Woo, I'm getting tired. U to the 3rd times u to the 20th is u to the 23rd. 3u squared times u to the 20th is 3u to the 22nd. 3u to the 21st plus u to the 20th. And then we can anti-differentiate each thing and get u to the 24th over 24 plus 3u to the 23rd over 23 plus 3u to the 22nd over 22 plus u to the 21st over 21 plus c. And then finally plug back in that u is equal to x minus 1 to get the kind of gross looking x minus 1 to the 24th over 24 plus 3 times x minus 1 to the 23rd over 23 plus 3 times x minus 1 to the 22nd over 22 plus x minus 1 to the 21st over 21 plus c. Okay. lastly, so I think what I am going to do is I think I am going to stop this video after the last algebraic method. And I think tomorrow morning, because it is getting a little bit late for me, tomorrow morning I'll make the second half of the video, which is the other types of integrals. So things that have trigonometry in them, specifically just trigonometry, or then mixtures like exponentials and trig, or exponentials and logs, or logs and trig, or whatever, like all the combinations and powers as well. So yeah, we'll do that tomorrow because my brain is starting to fade. So let's do a couple more examples and then we will call it a night. So algebraic substitution, I'll call this 5. So algebraic substitution, also called by some people power substitution. Also, I should mention, in class the other day, I talked about improper integrals, and I did ones where the function was undefined at like somewhere like 0 or 1 or 2. And although that is an example of an improper integral, it is not something that is typically covered in 17b. I think the only types of improper integrals we deal with in the 17 series are ones where infinity is one of the limits of integration. Although it's good to have seen that, you can probably ignore it. So let's look at something like this. The integral, and I'm going to write this the right way this time, of x over the square root of x minus 4 dx. So I'll point out you could rewrite this as the integral of x times the square root of x minus 4 to the negative 1. The point here is that there isn't a good choice for you, at least not in the usual context of I would love to pick something for you whose derivative is also in there. Not going to happen. So instead, I go to the next best thing, which is to pick a u that is stuck inside some other function. I'm totally going to pick u equal to the square root of x minus 4. I really shouldn't even bother finding d. I will, just for the sake of argument, because there is a way of doing it this way that some people like, not me. The du dx here is 1/2 x to the negative 1/2. Cool. Yeah, I don't even want to do it. I'll show you if you really want, but here's the better way of doing this. So when you get here, like, I don't have, like, if I try solving for du, I can rewrite this as 1 over 2 root x dx. I don't have a 1 over 2 root x dx. And yeah, I could manufacture one if I really had to, but I shouldn't. Here's the better thing to do. When you start going down this path and things get ugly, it is often good to say, I'm going to take my choice for u, and I'm going to solve for x, meaning isolating x. So add 4 to both sides. I should never pick 4. My u's and my 4's look too similar. But add 4 to both sides. U plus 4 equals the square root of x. And then square both sides. U plus 4 squared equals x. And then take the derivative of both sides. So the derivative of u plus 4 squared is 2 times u plus 4 to the first times the derivative of the inside, which is just 1. Du equals the derivative of x, which is 1 dx. And then that, you just get to say, I'm going to plug all of that in for dx, because dx is equal to that. And then I can deal with the rest. So I can say that I have the integral. It also does require some back substitution type methods, because you're going to have some leftovers here. So the square root of x minus 4 is my u. My dx is equal to 2 times u plus 4 du. And x, well, I also know what x is equal to because I did the work right here. X is equal to u plus 4 squared. And I would rewrite this as, I pull out the 2 in front, integral of u plus 4 squared times u plus 4 is u plus 4 to the third divided by u. And now you're kind of stuck. You have to multiply this out. Let's go ahead and give ourselves another piece of paper. I know I did on the other page, I did that kind of x minus 1 or x plus 1 cubed really quickly. In case you, just so you know, the way I did that was I used Pascal's triangle. When you have something plus something cubed, x plus 1. So in fact, let me just look back to make sure that's what I actually did. x minus, no, it was x, it was u plus 1 cubed. And it was very quickly u cubed plus 3u squared plus 3u plus 1. More generally, if you have something plus something cubed, it's always going to be 1 times the first thing cubed plus 3 times the first thing squared times the second thing to the first plus 3 times the first thing to the first times the second thing squared plus 1 times the second thing to the third power. That's how you multiply out some quantity like that cubed quickly. So now our integral is going to equal, I can probably put it in the bottom there. That's going to equal 2 times the integral of, I've got, let's see, u cubed plus 3 times 4 is 12u squared plus 3 times 16 is 48u plus 4 cubed is 64, all divided by u. And then we divide each thing by u. So I end up getting 2 times the integral of u squared plus 12u plus 48 plus 64 divided by u, which ends up equaling, okay, it's going to be close here, 2 times u cubed over 3 plus 12u squared over 2 is 6u squared plus 48u plus 64 times the natural log of the absolute value of u plus c. And then finally plugging back in what u was equal to, which was the square root of x minus 4, it's going to be not pretty at all. You're going to get the square root of x minus 4 cubed over 3 plus 6 times the square root of x minus 4 squared plus 48 times the square root of x minus 4 plus 64 times the natural log of the absolute value of the square root of x minus 4, all that times 2 plus c. Whew. So that's the example. That's an example of an algebraic substitution or a power substitution where you've chosen your u. It doesn't look like things work out very nicely that way. So instead, you solve for x in terms of u, and you find dx by just taking the derivative of that. Now, I will point out, if you try hard enough, you can avoid this usually. I could have done this and done the following. I don't love this. I don't recommend doing it this way. But if you're curious, you can watch this part. If you're not curious, you can not watch this part. And it's totally fine to be not curious about this. I wouldn't be personally. So from here, what you can do is you can do all the same work here, and then you can start rewriting. So my integral of x times the square root of x minus 4, I didn't want to really write it that way, but I did. Oh well. So I might do the thing where I see that this is du equal to 1 over 2 root x dx. And I might just multiply by that and say that dx is equal to 2 times the square root of x times du. And then I might say, oh, but look, u is equal to the square root of x minus 4. So if u is equal to the square root of x minus 4, then u plus 4 is equal to the square root of x. So I can kind of jam that right in there. It's really not any better. It's really not any different. You're still going to end up at the same place. You're going to end up at the integral of, in fact, you still even have to solve for x to do the back substitution. It's really, really not the way to do it. But if you want to do it this way, you could. You say, well, x is still going to be u plus 4 squared. And then square root of x minus 4 is u to the negative 1. And my dx is, well, dx was 2 times the square root of x du. But then the square root of x is equal to u plus 4 right there. So I end up with the integral of u plus 4 squared times u to the negative 1 times 2 times u plus 4 du, which is really exactly the same as this right here. Sorry, I'm off screen here. 1 second, apologies. There's no one to tell me I'm off screen. So, right, u plus 4 squared times u plus 4 is u plus 4 cubed times 2 divided by u, or times u to the negative first. So it's really the same integral. There's no good reason to do it this way. So I say don't do it this way. Do it this nicer being still not great way instead. So yeah, that's an algebraic substitution. They're kind of terrible, but they're not that bad. They're pretty bad. All right, so that is the end of the algebra section of this handout as far as we're concerned. And I'll try to, when I have a chance, modify this handout so it's more, and post it. I don't have it posted it. So I'll just point out in this handout, sorry, now I'm like all over the place here. I don't know, sorry, I'm like, keep saying sorry, I'm all over the place, and I am. Apologies, 1 second. Where did you go? Okay, here we go. So again, so far what we've covered in this handout is just the algebra section. We talked about making it a powers of x problem. We talked about does the derivative of one part equal another part, aka is it a u sub problem. We talked about tricks like long division. Sorry, it's getting a little blurry there. Partial fractions. And then we slipped in the 1 over x squared plus 1 stuff and the back substitution, which we already kind of talked about a little bit. And then finally, we didn't talk about trig substitution because that's not a thing we do in the 17 series, but we did talk about algebraic substitution, which is what we were doing here. So next time, in the next video, we'll talk about trig, mostly in the context of just u sub. So, right, kind of actually not this and not this. So there's not a lot of trig we really talk about in this class either. But then finally, after that, let's see my pages here. That's page 1, page 2, page 3, page 4. After all of that, we will talk about powers of tangent and secant, powers of sine and cosine. But then we'll talk about the mixtures. Mixtures being typically either done via u substitution or done via integration by parts. All right, that's all for this evening. This video is already much longer than I hoped it would be, but really expected to be this long. So good night. I'll see you all on Monday. Don't come to class on Friday.